Can you all hear me okay?
Yeah.
Okay, so yeah, regarding the labs, I understood a lot of folks emailed me kind of late saying that they're don't worry about it. Again, this is the first time I'm doing this kind of thing. So we're probably going to be ironing out the kinks as we go along. And I'll try to figure out what the best way to upload the labs. I think really the best way to upload the labs is to just put them straight to YouTube. I mean, when I put the lecture file for each of my lectures onto YouTube, it takes like 7-8 hours. Like like this particular lecture I'm doing now, as I'm recording it, by the end of class time, the file will be about 10 gigabytes. That's because I'm saving my file on a Mac, and my movie capture program only saves MOV files. If you can save it as a MP4 file, it'll be a smaller file. Yeah, and if it's on YouTube, it's fine. In multiple videos is fine. Okay. So we'll work it out. It might take me a while to find all of them and grade them, but I'll get to that. But yeah, like I said, you guys are doing this. We're doing this like the first time with you guys, and so there's going to be some things that have to be ironed out. So we just have to kind of be a little bit patient with each other regarding how this works. Yeah, there is software that can convert files. I mean that's what YouTube does. One of the problems with uploading to YouTube is you upload the file, it takes a while, and then it converts it to a smaller size file because they have to have a way to convert files because so many files are constantly being uploaded. Imagine the storage space they need for all the videos that they have from all over the world. So I changed the homework dates, and eventually I will re-upload your all the web assigned homework so that it reflects the correct dates. So if you look on the board, homework 4 is due on the 1st, homework 5 is due on the 6th, and homework 6, it's not 7. Homework 6 is due on the 13th, and there's an exam on the 14th. So this is a little bit of a faster unit, but the material is, at least I don't think, is bad. There's less calculus in this unit, so I hope it makes it a little bit easier. This is an important unit for those of you who want to learn about building circuits. Okay. Make sure you work on the multimeter quiz, and then again for the video, best thing to do is put it on YouTube. Especially if you could make one full file. Did you guys get the capacitance lecture notes? I thought I emailed with you folks. If not, I'll have to do it right after class. It's kind of hard for me to do it right now, but I can email the lecture notes. I apologize. Okay. Is it all right if I just do it after class? Okay. Sorry about that. I thought I emailed a bunch of them. There's two of these lectures, so I'll send them to you. Okay. Anyway, work on the multimeter quiz, and then I started working on the exams. I will try to get them graded as soon as I can. I have other duties on campus that's taking time away from me working on grading the exams, so you might have to bear with me. It also is slower to grade exams on Canvas. So usually if the class was on ground, I would have the exams graded already. Okay, but for some, everything's slower now, so I apologize for that. How was the exam? I got to ask that. Was it okay? Was it? And granted, I think it's going to be a little bit harder than what I would give on ground if we were in a classroom. Just because I can give more standard problems when we do the exam in class. No comments? It was a little hard to understand. Yeah, I mean, if you have questions on the exam, please don't hesitate to ask. I want to make sure you understand what it's asking. Okay. All right. So today what I want to do is talk about capacitors in chapter 26. And this is not a very long chapter. I mean, I can do this chapter in 2 lectures. So I should be done with this chapter by Monday.
Yes, sir.
Question?
For the multimeter quiz,
Yeah.
where I'm trying to look for it, I just found like a video for it and a file for it. Just to clarify, how would you like us to do that multimeter quiz?
So in the multimeter quiz, let me. I have the file open. I just gotta. Second. So in the multimeter quiz, on the second page, it has you go through an exercise. There's six items I need you to do. And you just, in the video, you got to show me that you can do those 6 exercises. That's it.
Good, perfect. Yeah.
Okay. And if you can in the video, fill out this sheet of paper. Show me that you filled it out. Otherwise, you have to submit the sheet of paper. That makes sense? Because it's going to have you do some calculations. Or you can write it, if you have a whiteboard, you can show the calculations on a whiteboard.
Sounds good.
Okay?
Thank you.
So you basically got to demonstrate that you can do all 6 items on this list. And I don't know if you look at the email, Tyler created a video, 10-minute video, on how to use the multimeter. So he actually went in the lab and carefully filmed how to make the measurements. It's kind of hard for me to do in the lecture. Yeah, if it's easier for you to submit the sheet of paper, go ahead. Okay, whatever works for you. Okay. If you want to submit it or write on, or use a whiteboard, or whatever, however you want to do it, or take while you're videotaping the lab, take a screenshot of what you filled out. That's fine too. Okay. And when you film it, you can stop the video. You can stop recording and then start. Like my software that I have here, I can actually stop recording and start again. I can pause it and start. So if your camera can pause and start, then you can make one continuous video. Okay. So let me change views. And I'll answer more questions on the lab. Okay. So these are the topics I want to talk about in this chapter. And what we're doing right now is we're making the transitions from electrostatics to charges that are moving in a system. Okay, so when we get this, and we've already talked about chapter 27 in the lab. In chapter 27 in the lab, we're applying the electric field to a wire. So there's electric field in the wire, and so the electrons will move, and then you get an electric current. So that's what we're going to be doing. We're going to go from static charges to moving charges, and then we'll talk about magnetic fields in the third unit. So, if you do an experiment and you apply voltage to a conductor, you can show that the total charge on the conductor depends on the shape of the conductor and the electrical potential on the conductor. For every conductor, you can show this. And so what we want to do is we want to define a quantity that relates the electrical potential to the amount of charge stored on each conductor in the system, or maybe the energy stored in the field. What we're going to do is we're going to focus on two oppositely charged conductors. They form something called a capacitor. And they're very useful in electrical circuits. So we're going to define the capacitance as the ratio of the magnitude of the charge on a conductor divided by the magnitude of the potential difference. It's defined to be positive. So basically what I'm saying is this. I want to define the capacitance so that it's a positive number. Q, so that's QC. And the magnitude of Q and the magnitude of delta V. That's my capacitance. You can define capacitance for a single conductor, two conductors, or five conductors. But we define a capacitor itself, a pair of oppositely charged conductors. And so this is how we define a capacitor. And they have a lot of practical applications in real life. For example, when you press the key on the keyboard, you're actually changing the capacitance. Okay. Or like you want to press the button for the letter P, you're actually changing the capacitance. If you're using your intermittent wipers on your windshield wipers, you're actually using the capacitor in that. The capacitor is actually used to for the timing of the intermittent wipers. Because you can on your intermittent wipers, you can set the wipers to come on every 3 seconds, every 5 seconds, whatever. And every time you change the setting, you change the capacitance. Actually, you can also change. I shouldn't say that. You can either be changing capacitance or resistance. So suppose we have a parallel plate capacitor. That's the simplest capacitor we could talk about. So what happens when you apply a voltage, a potential difference between the two plates of a parallel plate capacitor? Again, this is the device that stores energy. People will say it's a device that stores charge. And it's actually kind of a misnomer because if you look at the total charge delivered by the battery, guess what it is? Anybody want to guess? Based on that picture. You have positive Q on one plate, negative Q on the other. You get 0. Right? The total charge is 0. So to say that a capacitor stores charge is kind of weird, but really when we're referring to Q on the capacitor, we're referring to the charge on one of the plates or one of the conductors on the capacitor. Okay. But like I said, capacitor is two oppositely charged conductors. Capacitance itself can be defined for a single conductor, two conductors, three conductors, etc. And we're not going to do we're not going to do calculations of capacitance that involve more than two conductors. So let's say you connect the battery to the capacitor. So what happens? So let's start at the negative terminal of the battery. And the electron goes to the right-hand plate. Well, so if the electron goes to the right-hand plate, let me change the view here. If an electron goes to the right-hand plate, then the right-hand plate will have a single negative charge. But if you have a single, yeah, I just got a notice that I have bad internet. Sorry. So then the plate on the left sees the negative charge, and of course, it wants to have a positive charge, so it's going to pull up the electrons. Let me rephrase that. The electron on the plate on the left will go back into the battery. So now you have one plate that's positive, one plate that's negative. And as the negative side keeps getting charged, the positive side will also be gaining an equal amount of charge. An equilibrium is reached when the charges on the plates are equal but opposite, but also when the potential on the plate is at the same potential as on the terminal of the battery. So we can calculate the capacitance of a parallel plate capacitor. So let me state some assumptions in doing the calculation for the parallel plate capacitor. First of all, the dimensions of the plates are going to assume to be much larger than the separation of the plates. Okay. So that we don't have any issues with the field lines bending at the edges. We're going to assume for parallel plate we're assuming that dimensions of the plate much greater than plate separation. And what this means then is I have plates that are infinite in size. Okay. I want to look at infinite plates. And I know what the electric field is due to a set of infinite plates. Okay, so we're going to use that model to calculate C for a pair of parallel plates. But before that, let me say something about the units for capacitance. Capacitance is a coulomb per volt. Remember, a volt is a joule per coulomb, so Q over V is a coulomb per volt. It's a coulomb per joule per coulomb. And I'm not going to write the whole word out again. It's coulomb squared per volt. I'm sorry, per joule. And that's called farad. Named after Michael Faraday. So that's the unit. The unit of capacitance is the farad. This is a very large unit. In fact, if I were to use two parallel plates, to create a 1 farad capacitor, the 1 farad capacitor would probably be about the size of room S101, with the one plate being at the ceiling of S101 and the other plate being at the floor of S101. That's the approximate size of 1 farad capacitor. Now, there are special materials you can place in between the plates of the capacitor to drastically increase capacitance. And so you can actually create a 1 farad capacitor in a very small volume. I have an example. On this board, this green thing is a 1 farad capacitor. There's a material in between the plates called aerogel. An aerogel drastically increases the capacitance of the system. And we'll talk about this in the next lecture. Dielectrics, insulators actually increase capacitance of a parallel plate capacitor, or any capacitor, doesn't matter. So typically the units are in picofarads or microfarads. Those are typical values for capacitance. You rarely hear the term nanofarads. Okay, we usually talk about microfarads or picofarads. The term nanofarads is really not used. In the old days, the picofarad capacitor would be referred to as a microfarad capacitor. And nowadays they use picofarads. So let's say we have parallel plate capacitor fully charged. I want to calculate the capacitance of the system. So I have two oppositely charged plates. One has a positive charge per unit area, and the other one has a negative charge per unit area. Let me draw the field lines for each one. So the field lines due to the positive one, they all point away from the positive one. It's kind of like one of the homework problems we did in previous chapters. Let me draw the field lines for the negatively charged one, but they all go towards it. And I know from the previous chapter, I'm not going to derive this, okay? I'm not going to derive this, but the electric field due to a single plate is sigma over 2 epsilon naught. By the way, I apologize if the signal is not that good right now. Okay. So let me ask you a question. What's the field outside of the capacitor? It's 0. Now, what's the field inside the capacitor? Each one, they add together, right? So the field in between is going to be twice this number. So in between, the total field is going to be and again, I'm referring to the magnitude. It's sigma over epsilon naught. Okay. So the electric field then, I can write in terms of the charge density. And let me move here. So E total is going to be Q over A epsilon naught. Now the field is uniform in between the plates, so we can actually say something about the electrical potential between the plates. Since the field is uniform, delta V is E times the plate separation. Let's call the plate separation D. So if the field is uniform, delta V is E times D, the magnitude. Okay, we're dealing with only magnitudes here. So then I can substitute this into the equation, and I get delta V is going to be equal to Q over A epsilon naught times D. And then I want to solve for the ratio of Q over delta V. And when you do that, you get epsilon naught A over D. The further the plates are, the smaller the capacitance. Okay, the bigger the area, the more energy you can store between the plates. So that's the equation for the capacitance of a parallel plate capacitor. Again, this is always defined to be a positive number. So even though I didn't put the absolute value here, I defined my equation so that everything's positive. So I'll show you a simple example of a parallel plate capacitor. This is one that you would use in class. Looks like this. There are two plates. The plates are movable. We actually use this in a lab. There's a lab we normally do when we're on ground, where you actually measure the capacitance of the system as a function of D. Now, of course, this equation is not going to work when the plates are this far apart, because then D is going to be in the same order as the dimensions of the plate. So this equation will work, when the plates are fairly close together. Okay. Yes, the A. Yes, Patrick. The A is the area of the plates. So as you move this apart, this approximation starts to break down. So in the lab that you do, you plot the capacitance as a function of the plate separation. And you measure the area of the plates, right? Pi. You measure the diameter, pi d squared is the area. So if you measure this as a function of this, you graph it, and you can extract the value of epsilon naught from this experiment. And it's a cool experiment because you get to see how capacitance affects the system. Because you have to actually be very careful in making the measurements. Because even you touching it affects the result. Even the wires affect the result. The wires that go from here to the meter that measures capacitance will affect the results. It's actually a very sensitive experiment. And I'll show you why the wires make a difference. I'm going to do an example a little bit. Okay. So the one thing you see here is that C depends on A and D. It depends on the geometry of the conductor. Well, also, when we also talk about resistance in a wire, it also depends on the geometry of the conductor. Later on, when we talk about inductance, you'll also see that it depends on the geometry of the conductor. So these are three quantities you're going to learn this semester. It basically depends on the geometry of the conductor. Typically, these values are these expressions are tabulated in electrical engineering books. So you'll see this if you look at electrical engineering books. It talks about capacitances for various geometries. You'd see this equation here. You'd see one for concentric wires, or concentric cylinders, or concentric spheres, or maybe two cylinders that are separated by a distance d. You'll see all those equations tabulated somewhere. Okay. If we have time, I have to ask Tyler to make a video. But if we have time, there might be one on our YouTube website already. But I can ask Tyler if he has time. I can have him try it. By the way, the Sierra College Physics and Engineering has a YouTube channel, and Tyler's been creating YouTube videos either for labs or for demos. So if you search on YouTube for Sierra College Physics and Engineering, you'll see the YouTube channel with all the demos. Okay. So now I want to ask you a conceptual question. And I love asking these questions because it gets you to, I think it gets you to understand electrostatics better and also capacitance. So imagine we have a parallel plate capacitor and we charge it with a battery. Okay? So we charge a parallel plate capacitor with a battery. So this is a conceptual question. And what we're going to do is, while it is still connected to the battery, I'm going to increase the plate separation. So what happens to the electric field, delta V, Q, and C? So we have, and I'm going to draw a schematic diagram. This is the battery. Capacitors are denoted by two parallel lines, unless one of them is electrolytic. So you can define, you can write in a schematic diagram a capacitor like this. There's also a version that looks like this. This is an electrolytic capacitor. Okay. So either one of these represent in a wiring diagram, schematic diagram, a capacitor. So I want to increase D. So what happens to E, delta V, Q, and C? What do you think? Any thoughts? What happens? One of them is easy. It's still connected to the battery. So what should delta V do if it's still connected to the battery? Well, it ain't going to change, right? This doesn't change. Okay, but if this doesn't change and I increase D, what happens to E? This doesn't change, this gets bigger, this has to get smaller. So if this gets smaller, what happens to Q? Well, if the electric field decreases in E, or the capacitor sigma over epsilon naught, then this has to decrease. And then of course C decreases. Because if you make this bigger, then C gets smaller. Next question. Let's remove the battery. So let's charge it with the capacitor, remove the battery, and then increase the plate separation. Now what? Now what happens? One of them doesn't change. Which one can't change? Yeah, Q. The Q is not going to go anywhere, right? So this stays the same. What happens to C if you make D bigger? If you make this bigger, C is going to do what? Isn't it going to decrease? What about the electric field? What does the electric field do if you keep the charge the same? Remember, this is Q over A. What's that going to do? Yeah, it's going to stay the same. And what about delta V? E stays the same, D increases. This increases. Remember, this is related to joules per coulomb. Right? This is related to the amount of joules per coulomb, right? The amount of work per unit charge. So really, if this increases, you're actually storing energy. Where's the energy coming from? Where in the world is the energy coming from? Yeah, you're doing work. You are putting energy. By increasing the plate separation, you are doing work on the plates. And in fact, if you look at the electrophorus lab, if you do the electrophorus lab, and let's say, well, here's the electrophorus, here's the material you put it on. You take a light bulb and you touch it to this electrophorus, you might get a little bit of a flash. If you lift the electrophorus up and then you touch it to the light bulb, the flash will be bigger. And the reason why the flash will be bigger is because you've done work in lifting up this electrophorus. You've stored energy in the field between the two plates. You store energy in the field between the two plates. And so you're going to dump in more energy into a light bulb and it will brighter. Okay. So I want to do a more complicated example of calculating capacitors. I'm just going to do one. Okay. Actually, I'll do another one. I'll do one involving a single conductor. And that one's not going to be hard. So let's say we add two oppositely charged concentric conducting cylindrical shells. Okay? And I want to calculate the capacitance of this system. One of the things I like about these problems is it allows you to put together everything from stuff in this unit and stuff in the previous unit. So we have concentric conducting shells. Okay. And I want to calculate the capacitance of this. So let's say just for consistency here, if these are cylindrical shells, then we're going to have a charge per unit length on this called lambda. So let me call this one. I want to make sure I don't make it silly here. Minus lambda, and this is lambda. We did an example like this in the previous chapter. Okay. Yes, Aaron, I just saw your question. Yeah, that's why the system shocked you more when the plate was higher. That's a good observation. So I need to I'm not going to use Gauss's law and spend time deriving the electric field. But the electric field in between the conductors is 2k lambda over r. What's the electric field outside of two conductors? 0. Okay. Electric field out here is 0. Electric field inside here is 0. But the electric field here is not 0. It's given by this expression. In fact, if I wrote it as a unit vector, it would look like that. And in fact, we pointed bravely inward. For some reason, my notes do not measure. Match this picture. Okay, so in order for me to be able to calculate the capacitance, I need to calculate delta V. I need to calculate my delta V between the two. I need to know delta V from here to here. But delta V is minus the integral of E dot ds. And I'm going to integrate along r hat because then the electric field is parallel to r hat. I'm going to have a minus there and a minus there. And I'm going to integrate from C to B. Okay. And this integral is easy. It's a natural law. Now, before I continue, remember the definition of capacitance. Capacitance is the magnitude of Q over delta V. Now, these are infinitely long plates. So the amount of charge on, not plates, infinitely long cylinders. The amount of charge on the cylinders is infinite. So I'm going to have infinity over something, which is not going to make sense. So my capacitance is infinite. So what I'm going to do is calculate the capacitance per unit of length. So really what I want is the capacitance per unit of length. And the reason why, I'm going to write it this way. Q is going to be basically lambda times the length of the capacitor. And so C over L is going to be lambda over delta V. So in my particular case, it's going to be lambda over 2k lambda natural log of V over C. And so C then is going to be 1 over 2k lambda natural log of V over C. And I always write it as the absolute value to make sure this is a positive number. Now, I'm going to write down an equation, and so if you want to practice, you can. This is a good one to practice on. If you have concentric spheres, you can show that C is AB, let me go AB like K and A times B. AB are the radii, the inner and outer radii of the spheres. So what you might want to try to do is calculate the capacitance for concentric spheres. Just for practice. You can also do two cylindrical conductors separated by D. You may write that one. Okay, so if we do this one, again we got to do C over L. Like again, these are all tabulated variables. Okay, Patrick, I missed your question. How did you find infinite capacitance? You mean you're talking about here? The charge is infinite, right? On infinitely long wires. And so instead of solving for the total capacitance, I solve for the capacitance for the one. Okay. Yeah, anytime I have something infinitely long, I gotta do something like that. So if it's a two conductor that's separated by distance d, then this is the capacitance. And this dimension, big D, has to be much, much bigger than small d. And this is for concentric spheres. So these are for practice for you. So what I want to do now is talk about what happens when they take capacitors and connect them in a circuit. Suppose I take two capacitors, and it doesn't mean, they don't have to be parallel plate, whatever the geometry is. I take two capacitors. I mean, I'll always draw them as parallel plates. And I connect them together. The battery. Like that. What happens? So that's what I want to do next. Okay, but and I forgot to mention one thing regarding the concentric cylinders. The idea of the concentric cylinders is important when you're measuring small signals. The capacitance of the concentric cylinders. Basically, you have a wire with a shielding around it. Okay, you have a wire with a shielding around it. That system has a capacitance, and that capacitance becomes important when you're measuring very small signals like 10 to minus 12 ohms. Okay. This expression is important. These are two wires that are separated by a certain distance. So if you're measuring the capacitance of this guy, and you have a wire coming out from here and a wire coming out from here to a meter that measures the capacitance. If those two wires are close together, and this separation is significant, those two wires are going to affect the measurement. You actually have to have those cables that go from the plates to the meter to be separated as far as you can, because otherwise the cables are going to affect the measurements. When you do the lab, you can see it right away. You can bring it real close together and change your capacitance. But that's when the plates are fairly far apart. When they're real close together, capacitance is high. The wires are not, you're not going to see the effect of the wires. But as you increase the separation, the effect of the wires comes important. So it's a nice lab that teaches you about, sensitivity of some measurements. So this would represent that case, where you're actually measuring this with we have two cables coming off it into a meter. Also, if you touch it, you become part of the capacitance of the system. And you'll affect the system. Okay. I'm sorry, I did get a little bit ahead of myself regarding series and parallel. But let me do that now. Let me talk about capacitors and series and parallel. So what happens when I connect this? Well, negative charge, let's say negative charge goes here. The electrons on this plate don't like this guy. So they run away to this plate. This becomes positively charged, that becomes negatively charged. What happens to this guy? Well, it sees a positive charge, the electron wants to run away, so it becomes positively charged. The amount of charge gained by this one, the amount of charge, positive charge gained by this one is going to be equal to the amount of, the amount of negative charge gained by this one is going to be equal to the amount of charge, negative charge lost by this one. Charge gained equal charge lost. Charge is conserved. So the charge on each one of these conductors is all going to be the same. Conservation of charge. But this if this gains a negative charge Q, this has to gain a positive charge Q. If this gains a positive charge Q, this has to gain a negative charge Q. Does that make sense? The Q's are the same. But, you know, Q1 has to be equal to C1 times delta V1, and Q2 has to be C2 times delta V2. So the delta V's are going to be different across them. So let's say this is at 3 volts. This point here is going to be at 3 volts. This point here will be at 3 volts. So this point is going to be some intermediate one. I'll put B sub I for intermediate. And this will be at 0 volts. You can see that the delta V across this one plus the delta V across this one has to be 3 volts. So delta V of the battery has to be equal to delta V1 plus delta V2. The voltage drop across the first capacitor plus the voltage drop across the second capacitor has to be equal to the voltage drop due to the battery. Well, if that's the case, then I'm missing something there. And I can write this in terms of the Q's and the C's. Delta V of the battery can be written in a different way because delta V1 is Q over C1. And delta V2 is Q over C2. Now what I'm going to do is replace these two with an equivalent capacitor that yields the same charge on each plate of the equivalent capacitor. So then I'm going to replace it with an equivalent capacitance. The Q's cancel. And so what I get is 1 over C effective equals 1 over C1 plus 1 over C2. So I can replace those two with an equivalent capacitance given by this expression, and I'll get the same charge on it that's delivered by the battery. Same charge at each of the plates of the conductor, of the capacitor. And students have sometimes messed up with this because if you want to solve for C effective, it's 1 over C1 plus 1 over C2 the minus 1. So you got to take the reciprocal of C1, add it to the reciprocal of C2, and then take the reciprocal of the whole darn thing. Okay? That's what you got to do. And if there's 3 of them in parallel, then you would add another term. If there were 4 in parallel, then you would add another term. That's how it works. Make sense? So I have this derivation in the notes. Now, what if the capacitors are in parallel? We've already talked about what parallel means. It means that the voltage drop across each element is the same. Let me redraw the circuit for the parallel case. With my battery, let me draw my 2 capacitors. And again, I'm going to assume the capacitor values are different, okay? Normally when you draw these, it's always good to put in a switch. I never do, but you should have a switch. You have to switch. You close the switch and then you charge it up. Okay. So what happens if they're in parallel? Well, you know, if let's say this is a 3-volt battery, 3 volts here, 0 volts here. This points at 3 volts. This points at 3 volts. 0 volts. 3 volts, 3 volts, 0 volts, 0 volts. So the potential difference across each one is the same. So they both have the same delta V. They have the same delta V, but they have different C's. So that means they have different Q's. Because you know Q is C delta V. And that should make sense. That should make sense because you know when as you're charging it, let's say the electrons go through the blue wire here, and then it reaches this junction, then the electrons have to pick which side to go. So now the electrons have two different paths. So there's no reason why these two have to have the same charge on them. Right? There's no reason why the conductors on each one of these capacitors have to have the same charge, because you're allowing the electrons to take two different paths. And so the charge on this capacitor is different than the charge on this capacitor. But charge is conserved, so whatever is delivered by the battery has to be equal to whatever is here plus whatever is here. So Q. Okay, I was trying. My phone is acting weird there. Sorry. So my Q total is Q1 plus Q2. Okay. All right, so let's write an expression for Q1 in here. C1 delta V plus C2 delta V. I want to replace those two capacitors with an equivalent one that gives me the same total charge delivered by the battery. And again, the delta V's cancel. I mean, pretty simple. We have C effective. And so these are capacitors in parallel. And again, I have a derivation in your notes. They add. Capacitors in parallel add. Capacitors in series add as reciprocal. And here's the thing, when we do resistors in series and parallel, the form of the equation switches. Okay, so don't get confused with that. Okay, when we do resistors in series and parallel, the form of the equations will switch around. And that's because of the relationship between Q and V here, and then the relationship between I and V when we do resistors. But here's a review. If you have capacitors in series, no matter how many you have in series, the capacitors add as reciprocals. If you have capacitors in parallel, then they just add numerically. So we have enough information now to do really more complicated circuits. So instead of doing a bunch of simple circuits, I'm going to do one that's complicated right off the bat, if you guys don't mind. And what I'm going to do is, I'm going to give you a capacitance system which is fairly complex. The numbers are easy, so I'm not going to do a lot of math here on the board. What I'm going to do is, in order to solve a problem, I'm going to be basically focusing on this equation and this equation. And the other equation I'll be using is this, Q and C delta V. So basically I'm going to be using 3 equations to solve my circuit, and it's going to be a fairly complex circuit. So let's take a look at our circuit. So here it is. Let me blow up that circuit. And again, let me know if you're having, I don't think you're going to have trouble with the math, except at one point. At one point, I'll use the board. So you have this circuit. There's 4 capacitors in this circuit. What I want to do is replace all 4 capacitors with a single one, such that the battery delivers the same charge to each conductor of the capacitor, as in this particular case. That's what I want to do. The process is fairly straightforward. Wherever you can combine capacitors, do it. Okay, wherever you can do it easily, then do it. So when I look at this, I automatically see that there's 2 10 microfarad capacitors. There's 2 10 microfarad capacitors that are in series. Okay, so going back to my equations on the board, this one, they're in series, at 2 10 microfarad capacitors. I use this equation, 1 over 10 plus 1 over 10 is 2 over 10. The reciprocal of 2 over 10 is what? 5. So those 2 can be replaced with a 5 microfarad capacitor. So what I'm going to do is replace those 2 and redraw my circuit. There it is. Now I have 2 5 microfarad capacitors. Those 2 are connected in parallel. Well, parallel capacitors add. So what's 5 plus 5? 10. That wasn't hard, right? I chose the numbers to be easy. Okay, so I can replace those 2 with a 10 microfarad capacitor, and I'll redraw it. Now I have 2 capacitors in series. One's a 10, one's a 2.5. Okay, so maybe I have to do a little bit of math. I don't have a calculator on me. Let's pretend I don't have a calculator on me. So I want to use this equation. I'm going to do 2.5 is 5 halves. Now, if I want to write this, isn't 2/5 the same thing as 4/10? Four-tenths plus 1/10 is 5/10. What's the reciprocal of 5/10? 2. So, in the end, I can replace everything with that 2 microfarad capacitor. Now that I've done that, I can figure out the voltage on each capacitor, and I can find the charge on each of the plates of the capacitor. So let's do that. Let's focus on this one on the right. So how much charge is delivered by the battery? Well, charge is potential difference times capacitance. 10 volts times 20 microfarads, 10 volts times 2 microfarads, 10 times 2 is 20. 20 microcoulombs. So this capacitor, which replaced all the other ones, has 20 microcoulombs on it. But this capacitor replaced two of them that are in series. Since those capacitors are in series, they must have the same charge on them. So both of these had 20 microfarads on each of the conductors of the capacitor. If I take on the capacitor, does it matter which side is positive? Well, the side that's connected to the positive side of the battery has to be positive. And the side that's connected to the negative side of the battery has to be negative. And then in between, you gotta have the opposite sign. Now, if we want to find the voltage on each one of these capacitors, you gotta take, well, let me show you the equation again, just in case I'm going fast. You have to take this equation and solve for V, a delta V, which is Q over C. So it's going to be 20 divided by 2.5. If you do it on a calculator, it's 8. Okay. And then for the other capacitor, you do 20 divided by 10 microfarads, you should get 2 volts. And it should make sense because 8 plus 2 better be equal to the battery voltage. Now, that 10 microfarad capacitor replaced two 5 microfarad capacitors that are in parallel. So those two 5 microfarad capacitors are going to have, since they're in parallel, they're going to have the same voltage on them. And since these are both at 2 volts, the charge on them is 2 times 5 is 10. And the sum of these two, 10 plus 10, better equal to that 20. Okay, I went too fast there. These have the same voltage, 2 volts, which is the same as the one on the previous slide. The total charge, 10 times 2 is 20. This capacitor, that's 5 microfarad, the one on the right, replaced two 10 microfarad capacitors that are in series. So that means that the two 10 microfarad capacitors will have 10 microcoulombs of charge on each one. The voltage on each one is going to be 10 microcoulombs divided by 10 microfarads. 10 divided by 10 is 1. And so they're both going to have 1 volt on them, and the sum of the two voltages better be equal to 2 volts. So you see how I drew. You see how I drew the circuit every single time. Every single time I found something new, I redrew the picture. That's what you got to do. Okay. Do you guys have questions on this? A lot of the homework problems on Unit 4 are basically these kind of problems. So you notice how much information I got out of this problem. So when you go to WebAssign, in one of these problems, you might have like 20 blanks to fill out. Yeah, if two capacitors are in series, they have to have, each plate has to have, the magnitude of the charge on each plate has to be the same. That's true. Because charge is conserved. When you look at the homework problem, There's actually another set of questions I can ask. I can also ask how much energy is stored on each of the capacitors. But we haven't talked about that yet. So, but that's an easy thing because you're just plugging numbers into an equation. So are we okay with that? So what I'm going to do on Monday, I'm going to talk about energy in a capacitor. So I'm going to leave that for now. I'm going to do two more things. Number one, I forgot to calculate the capacitance of a single capacitor. And number two, I haven't showed you examples of capacitors. So let me show you some capacitor examples. I got 7 minutes left. So normally when we're in class, I take one, I get one of these and I pass it around to you guys. So basically what this is, well, you can see, this is a very large capacitor. It's basically a parallel plate capacitor rolled into a cylinder. So it's two pieces of aluminum foil, and in between there's a paper-like material, which it's designed to increase the capacitance of the system. Not only that, it also allows you to increase the voltage you can apply to the capacitor. So basically all these are just two rolled up sheets of aluminum foil, and in between the sheets of aluminum foil is just a dielectric. Now this one, its capacitance is 10 microfarads. This one's 10 microfarads. And you can charge it up to 1,000 volts. This is a very dangerous capacitor. So generally when you handle a capacitor, you want to always make sure it is shorted. Yeah, this is a pretty high, this thing can store a lot of energy. This is a dangerous one. You actually, what you want to do with these is short them. You should always keep them shorted until you use them. Because what happens is these things, because of the ions in the air, these things can actually charge up by themselves if you let them sit there for a long time. And if you touch them, you can get hurt pretty bad. Okay, especially if this was electrically connected ahead of time and you forget to discharge and you touch it, it'll probably kill you. This is something that'll kill you because it has a lot of energy stored in it. Okay. So anytime you're around big capacitors, you've got to be careful. I have another big capacitor. This one is, wow, this one's 100,000 microfarads. 0.1 farads, this is 10 volts. But these are very dangerous. These are much more dangerous. Usually when, in class, what I do is I do a demo where I have two 10 microfarad capacitors connected in parallel, and I charge them up to 3,000 volts, and I discharge them instantly. It makes a very loud sound. I don't know if I film it, if the effect would be as dramatic, but I'll see if I can get Tyler to videotape them, so we can see that. We can see the effects. Okay. A smaller one. I'll show you. This is more typical of what you use in smaller electronics. This is a tiny little one. Again, it's just basically what these are is just parallel plates rolled up into a cylinder. Okay. It would be nice if I could pass this around and have you hold it so you can actually see it. But that's all they are. I mean, this is a tiny version of it. And this little one this one's polarized, it's electrolytic. It goes up to 50 volts, 1 microfarad. It's really tiny. Okay, it's a really tiny one. And you'll use something like this later on in the semester. There's a lab that we do later on in the semester where you analyze circuits with capacitors. You'll use a small one. You won't use one of these. These are a little more dangerous. I have a friend that he's an electrical engineer, And he actually installs his own solar power systems at his house. And he had an inverter that converts the DC from the solar panels to the AC of the house. And one of the inverters went bad. And when we unplugged it, we saw an arc across the plug. That's because one of the capacitors is still charged. The capacitors are always very dangerous. Anytime you work with devices that have capacitors in them that are this large, you have to be careful because you can really hurt yourself. Let me do a quick demo, I guess, of energy stored in a capacitor. So I have battery. I have the 1 microfarad capacitor. The 1 farad capacitor. And I'm going to charge. Right now I have the switcher. I'm charging the capacitor. Okay. And what I'm going to do when I flip the switch, I'm going to make the light bulb go on with the capacitor only. Okay. When I flip the switch, the light bulb should go on. There's that context in the switch. And so the light goes on, and it'll stay on until the energy is lost by the capacitor. In fact, if you don't trust me, these are hard to take out. I'll try to take out the batteries. And the light bulb should still stay on. Just in case you don't trust me. Okay, so the capacitor is delivering all the energy. It took all the batteries out. I have a bad contact somewhere. So eventually the light will become dim because all the energy is drained from the capacitor. The amount of time it takes for that bulb to get dim is going to depend on the product of the resistance of the bulb and the value of the capacitance. And you can kind of see it's already dimmer. We're going to have bad contacts. Okay. It's kind of a cool demo. I'm going to do the same thing next time, but instead of using a light bulb, I'm going to use a flash bulb. I don't know if you guys are familiar with flash bulbs. In the old days, like in the 60s and 70s, the cameras had a flash bulb on them. So I'm going to dump, so the energy will be dumped very quickly. So I'll get a nice bright flash for you guys. So I'll do that next time. So one last thing is I want to do the capacitance of a sphere, one conductor. And I say, well, how do you do that? How do I calculate the capacitance of a single sphere? Suppose I have a charged sphere. Okay. The inside, let's say the inside is empty. It doesn't matter actually in this case. The surface is at potential V equals K Q over R. Now, remember the C is Q over delta V, magnitude. And you might say, well, where is the other conductor? Well, let's assume second sphere at infinity of radius of infinite radius, where delta V, where V final is 0. So that makes delta V between this sphere and the one at infinity equal to KQ over R. So then C is Q over K Q over R. So the capacitance for a sphere is R over K, which is 4 pi epsilon naught R. And we can actually calculate this another way. We can calculate capacitance another way, and I'll show you an example next time. All right, so I'm going to stop here, and then we'll meet at 11:10 for lab. Questions? By the way, the 210R class will probably be very short. I'll probably have some conceptual questions, that's about it. Because most of you haven't started the homework. All right, so no questions, so I will see you shortly.